Hi. Okay, so we are on to the rules for current, potential difference, and resistance in series circuits. So you know about current, you know about potential difference, you know about resistance. Now we're going to learn exactly how they all behave when arranged in a series circuit. Let's start off with a few questions. Can you just state 5 components that you could put in a circuit? Simple, just 5. Can you name 4 things that will change the resistance of a wire? Think back to the last lesson. What are the 3 units for? Charge, potential difference, and resistance. And the last one, 2 measuring devices in electric circuits. Pause, answer the questions, unpause when you're done. Okay, let's see how it works today. 5 components you can put into a circuit. I'm going to do this symbol to make it simple. There we go. You put a lamp. You could put a resistor. You have to put some sort of battery, perhaps. You could have a variable resistor, and why not? Let's just add in a switch. 4 things that change the resistance of a wire. The resistance of a wire can be changed by changing the length, changing the thickness, changing the material, and changing the temperature. The units for charge, potential difference, and resistance. Charge is measured in coulombs. C. Potential difference is measured in volts. B. And resistance is measured in ohms. Use the omega sign there. What are 2 measuring devices? 2 measuring devices that we come across are the ammeter and the voltmeter. Easy. Okay, we've seen this before, and hopefully you will remember that when we have a series circuit, these things that are traveling around, these are the electrons. And the electrons are traveling around, they're coming out the negative end of the terminal, and they're going round, they go through the bulb, and they go back. And they keep moving. And if you look at all of those electrons, where they are in a circuit, you can see that they're all moving at exactly the same pace. They're all moving at the same speed. They're all going one after the other. If they all go fast, if one goes fast, they all have to go fast. If they all go slow, one goes slow, they all have to go slow. It is all linked together. The speed, so the current in a series circuit is the same everywhere. And that's just what we're saying. The current is the same everywhere in a series circuit because there was only one route, that says route, my head's in the way, for the current to travel. So, for example, if this ammeter says 1 amp, this ammeter will also have to say 1 amp. And this ammeter here says 1 amp. If you know the current at one point in the circuit, you know the current at all points in the circuit if it is a simple series circuit. So, let's test that. If it's 3 amps over here on the left-hand side, well, what is it down here? And what is up there? If we have 3 amps here, that means we have to have 3 amps here and 3 amps here. That's why that one. If this is 3, that one will be 3, and that one will be 3. What about this one? If we've got 11 amps here, doesn't matter whether it's at the bottom, the left, or the right. If that's 11, this one has to be 11, and this one has to be 11. So the current in series is so easy. If you know one, you know them all. The voltage in series is a little bit more involved. If you look at the voltmeter, it's measuring the voltage. We see if we put the voltmeter across the battery, it measures 9 volts. Let's see if I can get this to loop back again. So this bulb here, 4.5 volts voltage going across this one. This one here, move it across, 4.5 volts of potential difference going across that one as well. When we go back to the cell gives you 9 volts. So you can see 4.5 plus 4.5 equals 9. If you add the 2 components, you get the same as the bulb, or the other way around. Whatever you have, if you add the 2 components, you get the same as the battery. Whatever you get from the battery has to be shared between the components. In series, the voltage from the battery is shared between the components. If all the components are the same, it's the same voltage. And here we have an example. We have 3 resistors. So here is resistor number 1, resistor number 2, and resistor number 3. Because they're all the same, the voltage across them will be the same. And so this gives us 6 volts of potential difference from the battery, meaning you get 2 volts across this one, 2 volts across that one, and 2 volts across that one. So in a series circuit, the voltage from the cell, the potential difference, is shared between the components. If the components are the same, it's shared equally. If they're not the same, it is not shared equally. Here we have 9-volt battery. We have this one is 3 volts. This one is 3 volts. So what is this one going to be? It is also going to be 3 volts because 3 plus 3 plus 3 is 9. Here we have a scenario where they're not the same. This one is 5. This one is 2. We get 10. So 10 minus 5 minus 2 means this one will have to be 3 volts. 3 plus 5, 3 plus 2 plus 5 is 10. Which is the bigger resistor? Different question. This one here, this takes 5 volts of energy of potential difference to push through, so which is joules per coulomb. So because that has the largest voltage, that means the electrons have had to work the hardest to get through this one. So this one will have the biggest resistance. This one here is a small, only 2 volts. So the electrons haven't had to work very hard. So this one will have the smallest resistance. And this one, 3 volts, have a medium-sized resistance, because those are directly related. If you have a larger resistance, it requires more potential difference to push through. Now, when you put resistors together in series, what actually happens is they act like one big resistor. So here we have a diagram of resistor R1 and resistor R2. And when we have them together in series, we actually just think about them as one resistor RT. And to work out the total, you just do R1 plus R2. So this RT is equal to R1 plus R2. If we add a third one in here, it would be R1 plus R2 plus R3. In series, you just add the total number of resistors, the total resistance together. So what's the equivalent resistance in this circuit? Well, we've got 5 plus 10 plus 15 equals 30 ohms. And that kind of makes sense. Again, we think about resistors as some sort of obstacle. If you start here and you're working your way through this obstacle is the easiest one, 5 ohms. So you don't use up all of your energy. But when you come to the next obstacle, you have to have done the first one to do this. So you're going to be tired from this one. So, you use a bit more energy. And then this one, even bigger resistor. So you have to use even more energy. So when you're doing these obstacles in sequence, they all add up to one big obstacle. So by adding resistors together in series, they add up to give you a total resistance. Now, easy. Let's try and do some of these things. Calculate the potential difference across the cell in the circuit below. So here's the cell. The cell puts the potential difference into the circuit. It goes around. If this bulb takes 0.8 volts, and then this one takes 1.2, how much did the battery or cell give it in the first place? Pretty simple. This bit here is trickier. Explain the difference between current and potential difference. One's talking about flow, the other one's energy per something. In the diagram below, explain why the voltmeter connected across a short section of wire shows 0 reading. When I put my voltmeter here, it doesn't record anything. Why? Next one. The voltmeter is now connected across a much longer section, but still, like say for example, maybe like this. It now does read something, but a very, very small amount. Why? Why would it read something if you make the wire much longer between those two terminals than not? New bit. What is a series circuit? Can you define what a series circuit is? And what are the rules for current in a series circuit? What are the rules for potential difference in a series circuit? And then, can you work out the potential difference across the battery in this circuit? And then, can you work out the potential difference across the resistor Q? Easy. Done? Nice. Simple lesson. Answer all the questions. Good luck. I believe in you. Love you. Bye.